trying to keep my head down. Should be both.
Oh, nuts.
Yeah, we would love to go out there. Ladies and gents, if you will return your seats so we can get rolling with tonight's featured presentation. Ralph McHugh is a special guest for us tonight. So, if everybody could migrate back and sit back, and we're going to visit someplace very cold. Most planets.
Our speaker tonight is from the University of Michigan, Astronomy and Physics program, Dr. David Gerdes. Briefly, I'll run down. He has an extensive biography online. I'll just mention some of the highlights here and explain his program himself. He received his PhD from the University of Chicago. He's been a faculty member at Michigan since 1998. He began his career working on particle physics with colliding beams. Collided with two beams. But has moved into astronomy and astrophysics over the past dozen years. Currently, his main research effort is centered on the dark energy survey, which is using the 4-meter Blanco telescope in Chile. He's carrying out a 5-year survey of 1/8 of the sky. While the primary objective is the accelerating universe, the survey also turned out to be a powerful tool for mapping the solar system, and that's what he's going to be talking about this evening. Welcome our speaker.
Ralph, and thank you for the invitation. It's really a pleasure to be here, and especially it's a pleasure to meet people who are clearly interested in the solar system. This will be a talk about a significantly cooler place than Venus, and I mean that in a nice, awesome way. It's also nice to meet so many amateur astronomers. You know, as Ralph mentioned, I'm an adult onset astronomer. I got back into astronomy and astrophysics about 15 years ago, but I actually was an amateur astronomer when I was a kid. And I have the photographs to prove it and the hair to prove it. It was 1977. But that's me in the driveway of my home in Northeast Ohio with my little telescope. So I'm going to talk about what I consider a piece of opportunistic science that we are doing in the process of taking a data set intended to do a very different piece of science. We're trying to study why the expansion rate of the universe is accelerating, which is a great project, and that's a whole, another talk or a couple of talks. But we need to look out through the solar system to take this data, and because it takes a long time to get enough data to understand how the universe is accelerating, you develop a time series of data, and so things move around in the period that we're taking the survey. So to situate ourselves in the trans-Neptunian solar system, I thought I would just start by telling you a little bit about Neptune, the last planet. So here's the view from Voyager 2 back in 1989 as Neptune was coming into full view. And Neptune, as many of you may know, is the first planet to be discovered through mathematical inference. So it's a calculation that still, amazes me as a tour de force, that with data from the mid-1800s and calculational techniques that were available in the mid-1800s, it was possible to study the deviations from predictions in Uranus's orbit and say, there's something else pulling on it, and not only that, that thing is probably about there. Go look in this about 10 or 15 square degree patch of sky and there might be something interesting. And so Neptune was discovered that way. It's in a nearly circular orbit, about 30 astronomical units from the sun. And just to kind of explain our distance scales in the solar system, an astronomical unit is the mean distance of the Earth to the sun. So we're 1 AU, and Neptune is 30 times that distance away from the sun. So that kind of sets the scale. Neptune is also kind of geometrically in between a planet like the Earth or Venus or Mars for that matter, is sort of mediumly small rocky planet, and the gas giants like Jupiter. So it's, 17 times more massive than the Earth, about 17 times less massive than Jupiter. So that's where the solar system stood from 1846 until 1930. And in 1930, the first trans-Neptunian object was discovered. They didn't know it then that they were discovering just the first member of the Kuiper belt. But in case you can't clearly see the detection in this photograph, there is a small dot right here on January 23rd, 1930, and then 6 nights later, that dot is gone from there and it has moved over here. And that's Pluto. Just a few more observations and you can put them together and make an orbit. But that's the discovery of Pluto by Clyde Tombaugh, whose ashes just were flown by Pluto on New Horizons. There's a little piece of him out there now. The outer solar system has been of great interest to the public, since long before New Horizons came and got everybody interested in it again. In the late 1800s, people were excited to look for Planet X, and the search for things out there was in the news. And so this was front page news in the New York Times. 9th planet discovered, first found in 84 years, and so they go on. But if you read a little more, down the column there, you see things like the sphere is possibly larger than Jupiter. So you can't believe everything you read in the paper. It's different from the internet that way. Planet X, but a month later, they're saying, this is a little bit unusual. It's not like the other planets. They say that the computation, the orbit is strange. The eccentricity of the orbit, they say, is slightly more than 0.9, which is also wrong. It's much less than that, but it was a lot larger than the other planets. I think it's interesting that they say the inclination is 17 degrees 21 minutes. That's a lot of significant figures for a front page news story. But anyway, so Pluto was almost right from the beginning was recognized to be something quite unusual. They say maybe more like a comet, perhaps, than a planet. So let's fast forward now to 2006, and there goes the New Horizons spacecraft on its way to Pluto. It was the fastest object ever to leave the Earth. It was going nearly 60,000 kilometers per hour when it left the Earth. It crossed the orbit of the Moon in about 9 hours. The Apollo spacecraft took 3 days to get up there. So this thing, they had to make it go that fast so that it would get to Pluto before all the investigators on the mission died.
That's good. That's great. Yeah.
So there it goes. It took about an hour to do that, and that's great, except later that same year, Pluto was demoted. It was demoted because in the meantime, a lot of other things had started showing up out there in the trans-Neptunian solar system. Things that were every bit as planet-like or not as Pluto. Pluto turns out to be one of about over 1,000 currently known and presumably many thousands more yet unknown objects out there in that trans-Neptunian region in approximately similar orbits. And I'll say a little more about what I mean by these approximately similar orbits. So the International Astronomical Union, in a famous vote, decided that Pluto is no longer a planet. It's a dwarf planet. And there's a definition of what all that implies. But these nuances were sort of lost on, sort of the third graders who sent hate mail to Neil deGrasse Tyson. Not only that, civil unrest broke out. There was rioting in the streets. How many of you just, you all follow this stuff closely. How many of you were sort of a little pissed off that Pluto was?
Yeah.
You know, right?
Not a bit.
But I will explain the sense in which Pluto is very much a member of a class rather than something unique. So let's just situate Pluto within the context of the outer solar system and the Kuiper belt. So here's the inner solar system. There's the orbit of Jupiter in orange. the main asteroid belt between Mars and Jupiter, and then the inner planets in there. But this is all just a kind of small part of the larger outer solar system. So there's the orbit of Pluto. You notice it crosses the orbit of Neptune, and that's interesting. I always saw pictures like this and wondered why they don't ever crash into each other, and there's a good reason why they don't. And then, but this in turn is just an even, we know of much more distant things than Pluto now. The longest period known minor planet that never comes anywhere near Pluto, even at its closest point, is the dwarf planet Sedna, which is in a 12,000-year orbit that looks like this relative to that of Pluto. And it happens to be relatively near perihelion right now, which is why it's bright enough to be seen. There's presumably more such things out there. And then finally, Sedna is thought to be just perhaps the innermost member of this hypothesized Oort cloud that's kind of at the boundary of interstellar space and is the source of the very longest period of comets. So that's kind of where we're looking. I'm interested in this area that we might say kind of is in this box here, and what we can find looking out in that direction. So the Kuiper Belt and the inner Oort cloud, this region beyond Neptune, is actually a quite dynamically interesting region. That means that it's not just kind of a bunch of stuff. There's a lot of structure to it out there. So roughly speaking, you can divide this region into about 4 different populations of minor planets. The classical Kuiper Belt objects, the things that were discovered one after the other in succession starting in the 1990s, they form a kind of a donut-shaped, a toroidal disk that ranges from about 35 AU, sort of, remember Neptune's at 30, up to about 50 AU. And there's a pretty sharp break after 50. So it's quite confined. Short period comets are things that get kicked out of the Kuiper Belt through some kind of perturbation and fall into the more inner solar system. So classical Kuiper Belt objects are stable. They're in stable orbits for the most part because they're in relatively low inclination, relatively circular orbits that never get very close to Neptune. So Neptune dominates its region gravitationally, and if you get too close to Neptune, you can get kicked out of wherever you are and get kicked into a either in or out. So one way to avoid that happening is to be a classical KBO. You sit in a kind of safe, stable distance away from Neptune. Another way to avoid a close encounter with Neptune is to be in what's called a mean motion resonance with Neptune. That means orbit a certain number of times for every certain number of times that Neptune does in such a way that you may cross Neptune's orbit, but when you do, Neptune is never there. The best example of that is Pluto. So Pluto is locked in a 3-to-2 resonance with Neptune, so that whenever Pluto orbits the Sun twice, Neptune orbits the Sun 3 times. And that's why when it crosses Neptune's orbit, it never actually encounters Neptune, because Neptune is one of 3 places that none of which is near Pluto. So another way to be in a stable orbit is to be in a resonance that protects you from ever getting close to Neptune. If you're not in one of those things, then you will eventually have a bad day and get near Neptune and get scattered into some high inclination, possibly much larger Sun major axis orbit, and those have no, particular pattern in them. They can go out to hundreds of AU. And then finally, the last and perhaps most interesting way to avoid a close encounter with Neptune is to be Sedna. Just to have such a distant perihelion, 80 AU, that you don't, the whole solar system kind of looks like a point mass. So here in a little more detail is what that structure looks like, and let me talk you through a couple features of this plot. So here's Sun major axis on this scale, and it's a logarithmic scale, so this is 30 here, 100 here, 1,000 here, so these are getting to be very big orbits out here. And then I'm plotting eccentricity, the stretchiness of the orbital ellipse on the vertical axis. So what's going on here? So here is this line at 30 AU is the distance of Neptune. The dots show the orbits of known objects in the Kuiper Belt, at least as of about a year or so ago. And so there's Neptune. Here are all the Plutinos, Pluto and its ilk, in 3-to-2 resonance. So that's all piling up at a semi-major axis that's just inside 40 at a range of different inclinations. Okay? So that's what I mean when I say Pluto is an exemplar of a class, but it's not at all unique. There are a couple of hundred known things in this same 3 to 2 resonance along with Pluto. It's the most filled up resonance. So there's a few other higher order resonances, 2 to 1. They're called Tutinos, and there's the 2 to 5, and there's a number of other kind of sparsely populated ones. So those form these lines on a plot like this. The cold classical Kuiper belts are this big lump down here. And this curve here is showing you an object that lies along that curve has a perihelion of 40 AU. So I just kind of picked 40 arbitrarily as a typical Kuiper belt perihelion. You see there's not too many things that fall outside that line, below this curve. This would be objects that never get closer than 40 AU. So aside from a fair number of them down here, not so many of these things do. That's why Sedna and another interesting object called 2012 VP113 are kind of special. So this is saying that almost all these objects, even the ones that got kicked into very high eccentricity orbits, thank you, that got kicked into these very high eccentricity orbits, at some point in their orbit, get pretty close, get within kind of hailing distance of Neptune. So that's telling us that Neptune, in some sense, probably put these things there. These are all the scattered objects. Whereas these things up here, like Sedna and VP113, are a bit of a mystery. And so, what's going on at 40 AU here? We've actually been there a few times. Voyager 1, the companion of the Voyager 2 that took that Neptune picture I showed you, was on its way past the orbit of Pluto, around 40 AU. It didn't pass Pluto, but it was passing that orbital distance. And I think it was Carl Sagan, who someone may correct me, but I think it was Carl Sagan who actually helped convince NASA to turn the cameras on Voyager 1 around and point it back towards the sun. The NASA engineers weren't too excited about pointing the cameras at the sun, but Carl Sagan convinced them it would be safe. And the reason was that Earth was at its point near its point of greatest elongation at that time, and the thought was you could see Earth. And so this is a picture of Earth taken from 40 AU by Voyager 1. So these rings that you see here aren't the rings of any planet, it's just glare in the optics of the camera. But that's the Earth. Carl Sagan wrote a lovely essay about this photograph called The Pale Blue Dot. It's well worth the read if you haven't seen that before. So at 40 AU, the intensity of sunlight is 0.1%, what it is on Earth, or it's 75% of the intensity of sunlight in Michigan in January. The apparent size is about the size of a dime as seen from, say, the back of the room or so, 35 meters away. And Earth is just kind of a little dot lost in its glare. Okay, so we're looking back from here out to 40 AU and beyond. What are we doing that with? So this is where our experiment comes in. So dark energy survey. Obviously, from its name, it was not intended to do anything related to the solar system. So the Dark Energy Survey uses the 4-meter telescope at Cerro Tololo Inter-American Observatory in the Chilean Andes at about 7,000 feet inside this dome here. The telescope itself is pretty old. It was built in the late 60s, early 70s. Optics kind of endure forever, and what has changed over the years on this thing is its instrumentation. In the old days, it was photographic plates and things like that, and now it's modern CCD mosaic camera. So it is one of the most astronomically dark skies on Earth, and it's just a privilege to go there and go outside when the moon is down, because believe it or not, this photograph is not too different from something your eyes might see. The Magellanic Clouds stand out clearly. The Milky Way, including structure in the Milky Way, is clearly visible. It's just there's a Southern Cross. It's a remarkable place to be. So what we did, we meaning this collaboration that I'll show you in a second, built a new instrument for this camera, a 3-square-degree field of view camera with 570 megapixels, the largest, at least at the time, the largest astronomical mosaic camera in the world, DE-CAM. And the goal of the survey is to take photographs of an eighth of the sky in 5 colors to a limiting depth of around 24th magnitude. Now that takes some time. So we have been awarded, through the review process, 105 nights per year over 5 years between 2012 and 2018. So we are about to complete the third of 5 years in a couple of weeks. So we're on the sky roughly from August to the middle of February. And the purpose of collecting this data set is to perform measurements that will measure the expansion history of the universe over about the past 6 billion years. I think of it as sort of making a time-lapse movie, not that we're actually literally seeing anything expand, but the universe is completely static on human timescales. But we're looking back through different slices in distance as we look back in time at more distant objects. So in that sense, we can see structure and evolution of the universe unfolding in one big snapshot. So the purpose of this experiment is to answer the question, why is the universe accelerating? And that's a very interesting question, and I can say a lot about the measurements we're making, but that's a topic for a different talk. So here's who we are. It's a big international collaboration consisting of institutions from the US, Spain, the UK, Brazil, Switzerland, and Germany. Several hundred senior people, including students and postdocs. Great opportunity for graduate students to get their hands on some fabulous data. So if you go inside that dome, that's what you'll see. So it's the 4-meter telescope on a big, giant equatorial mount. So this is the yoke about which it turns in right ascension. The equatorial axis, the declination axis, is here at about a 30-degree angle. Okay. And up here, at the business end of it is DE cam, and here's a somewhat better look at it. Here's now looking from the side. So this thing here is what we built. That's the 570 megapixel camera with correcting optics to create this flat field of view over 3 square feet. The first lens in that camera is shown here when it was sort of off the initial casting and Corning back in 2008. And then 3 years later, they've been fully figured and polished. So there's 4 more smaller optical elements inside that camera. And what they are doing is focusing the light onto this CCD imager. So the imager consists of 62 8-megapixel chips arranged in a kind of hexagonal mosaic like this. So that's what an image of the focal plane might look like. And then the full moon would be about that big on the scale. I know you're all keen observers, and so I want to say a little bit about what observing is like on an instrument like this. It used to look like this. This is Hubble sitting at the eyepiece of the Mount Wilson 100-inch telescope back in the 1920s, studying the expansion of the universe back then. And here's what it's like now. So we don't have enough screens in our control room, so we all bring our laptops so we can, get some work done. We have coffee. But we sit in this nice climate-controlled control room, and the telescope does the work. You're not allowed up in the dome when you're observing, because you don't want the heat and the moving air and things like that. This camera takes beautiful images. This is an image taken on the first night of operation back in September of 2012. It's actually that spiral galaxy that you might have noticed in the lower bit of that image I showed you before of the full mosaic. So this is a spiral galaxy in the constellation Fornax. And the interesting thing about this camera is how well it worked more or less out of the box. And it was an interesting cultural experience on this collaboration for me too. I came, and many of my colleagues came from the world of experimental particle physics and high energy physics. We're kind of physicists first, and we're used to building big experiments. And then the other half of the collaboration is astronomers. A lot of them worked on the Sloan Digital Sky Survey and came up through the astronomy side of things. And so the physicists were like, well, of course it worked. Why wouldn't it work? We simulated it, we tested it, we designed it carefully. A lot wouldn't work. And the astronomers were like, holy crap, it worked! Things never work. It usually takes a year.
Yeah.
But it worked really well. Of course, it's gotten better over time as we find little things and fix them. But this is an experiment that was designed to do cosmology, this kind of extragalactic stuff. And so here's a test. This will help you see if you might be a cosmologist. So here's another image from DCAM, and so here's how to tell if you're a cosmologist or not. So what is this? Is this a bright, beautiful comet, or is it B, an annoying foreground object, obscuring all the interesting high redshift stuff behind it? If you think it's an annoying foreground object, you may be one of my colleagues. But if you think it's a bright, in fact, we didn't know it was. So this is Comet Lovejoy. This is from October of 2014. And how many of you saw Comet Lovejoy? Did anyone get out and see? You can see it in binoculars. It wasn't quite a naked eye object, but we have this super complicated computer program that figures out which exposures to take when, and that plots the whole sequence, what filter, what depends on what's rising, what's setting, where the moon is, what the seeing condition is, what we saw last night. This whole complicated flow chart. Well, we didn't know that the comet was there until people start saying, why did all these exposures get declared bad? There's all these pixels that it's saturated. Oh, there's this thing there. So it knew, everything about where the survey was, but it didn't actually know that this thing was going to be in there. Nevertheless, this was not the first time that an interesting solar system object has been seen by DCAM. Once in a while, we get an email like this. So this is an email from somebody at JPL to the director of the observatory. Say, I'm writing you to request director's discretionary time to get images of a critical near-Earth object. It may be on a potentially hazardous orbit, but no other surveys have been able to recover it, blah, blah, blah. It's cloudy in Hawaii. So can you try to locate this thing? And our camera is actually good for that. Near-Earth objects are typically discovered on maybe a single night over a period of a couple of hours, and so their orbital uncertainties blow up rapidly. So they can easily get lost unless you have a wide field instrument and can follow up pretty quickly. So DCAM was good for that. So we took 10 minutes out of our night to go look for this thing, and there it is. Can you see it? This is a roughly 100-meter diameter rock, roughly 30 million miles away at the time this picture was taken. Thanks to these images, it turned out that this object missed us by 18 million miles, and I'm happy to say that it therefore posed no threat to DES operations. Okay, so, but the most exciting thing from the solar system that was discovered very early on by DES, at least so far, led to the first Nature paper from DCAM. As you may know, Nature is kind of the premier science journal. If you publish in Nature, you've made it. And so here's the first Nature paper from DCAM. Another Sedna-like thing with a perihelion of 88 ADAU. Unfortunately, it wasn't by us. It was, we have a third of the time on this instrument. The other 2/3 of the time is available to other astronomers through the normal proposal process. And these guys were looking for Kuiper Belt objects, and they struck gold on almost the very first night that they were using it. So they found 2012 PP113, that other dot that was in the disconnected region. So what could we, so this kind of thing got me thinking, and at the same time I had recently, I had no plans to work on the Kuiper Belt, but at the same time I had just agreed to take a couple of undergraduates on as summer students. And I thought, I better figure out something for them to do. And I thought I should pick a project for undergrads that's not swarmed on by other people. I don't want to give them just a little piece of some big complicated project that's going to take 5 years and they don't really plug in before it's time for them to go again. I wanted to pick something that would be kind of fun and easily understood and had a chance of being successful. And so I thought maybe we could do something with the solar system. No one else is looking. If they don't find anything, if the project fails, it's no big deal. But it might be fun to go look, and if we're lucky, maybe we'll get to say we found a little piece of the solar system. So what could we do? So here's the sky in ecliptic coordinates, and the blue dots are, again, those blue dots that represent the positions of known objects in the Kuiper Belt. This kind of tank-shaped thing here is our survey footprint. That's our 5,000 square degrees. That's the eighth of the sky that we're doing. Now, our survey is actually two surveys. It's two surveys kind of interleaved that go on simultaneously. The first is the 5,000 square degree, eighth of the sky survey I told you about. That's the pink thing. But embedded within this are 10, you see these little green circles here, these 10 little green circles. Each one of those circles is an individual DCAM field of view, and we visit those 10 areas about once a week. So every spot in the wide survey is visited, a few times every 6 months. So not the temporal cadence of those observations is pretty sparse. But these are visited about once a week because we're looking for supernovae. We're looking for type 1a supernovae, stars that get bright and then they fade out over a period of a couple of months. And that's for our cosmology program. So we have a nice time series of data of these supernova fields. And I thought maybe we could look, now what moves slowly enough to stay in those fields over a whole season, objects in the Kuiper Belt. So let's look for things there. So that's what we decided to do. I just want to briefly say, here's how we describe an orbit. It takes 6 parameters to describe an orbit, the size and orientation of this ellipse and where the thing actually is in its orbit. So it takes 6 parameters to describe this orbit, and it turns out that you can uniquely determine, with varying errors, but you can at least get a solution to an orbit with observations on 3 different nights. So if you have 3 points, you can fit an orbit. So that's what we're looking for. And so in these supernova fields, that's a good place to do it. And I just was encouraged by the fact that we noticed lots of moving things in these supernova fields. Some of the fields, we take a sequence of exposures, kind of every couple of minutes for 15 minutes, and in different filters. And so this is showing the rate of motion on the sky in some units. And the blue dots are things that were known as main belt asteroids. The red dots are things that were not known, but are clearly more main belt asteroid. And these little crosses over here are somewhat more distant asteroids that are companions of Jupiter that we found. So, why are there so many things, why are so few of the things that we see known? And here's the reason. So here's the magnitude distribution, and I think you all know about magnitudes and how in astronomy bigger numbers mean that they're fainter. So, so the known ones here, the blue dots, are kind of 20, 21st, maybe up to 22nd magnitude. And all these new ones that we found are kind of peaking here at 22 to 24. So we're going much deeper than current catalogs of known asteroids would suggest that we can do the same kind of a thing and make the same kinds of relative gains in the Kuiper Belt. So how do you look for Kuiper Belt objects? Here's what we do. So the supernova group, the people looking for supernovae, have perfected a technique that goes back, in a sense to like people like Clyde Tombaugh sitting in dark rooms with something called a blink comparator, comparing images on different nights and seeing what's changed. So that's incredibly tedious, but fortunately computers get really happy if you just ask them to compare images. So what we do is when we take a new set of pictures of a supernova field, we take those new images and subtract from them an image of the same field taken on some date near the beginning of the survey. In principle, when you subtract the new image from the old image, what's left is everything that's changed. And so this is called difference imaging. And so when you do that, you have a search image. Whoops. So you find a whole big lot of transients. So here is from one particular visit on one particular night to one of these 10 fields. Each of these dots represents something that was discovered in image subtraction. A lot of them are main belt asteroids. Some of it's junk. Some of it's supernovae. And the question is, which of these dots might be Kuiper Belt objects? And the thing is then, take the picture of the same area on another night, a week or two later, you get a whole bunch more dots. Which of those dots are the same thing that's moved from here to there? And 2 weeks later has moved from there to there. So it's just sort of a, you know, a combinatoric problem. The computers also get really happy when you ask them to fit orbits. So, so that's what we do. And so, fortunately, you kind of know where to look, you know, because you know, suppose I want to know where might this thing be in a week. It's not going to be moving in some random direction. The reason is this. The Kuiper Belt objects are moving much more slowly than we are. They're in orbit around the sun, way out there, so they're moving pretty slowly. Their apparent motion on the sky against the background of stars is dominated by the motion of the Earth. We're observing these things from a moving platform, so what we're seeing is parallax of these things moving against the fixed background of the star. So if the object were stationary, it would just trace out an ellipse on the sky as the Earth goes around the sun. So depending on what time of year it is and where you're pointing the telescope, you kind of have a direction to look along for the next week. Now, in reality, these things are also, you know, moving in their own orbits, and so this ellipse doesn't close; it kind of loops like that. But over short durations, you can sort of use this parallax motion as a way to define a search region. We're on the sky, kind of from here to here when they're in their retrograde phase of motion. So if you find 3 points on 3 different visits that are connected in some parallax-like appropriate way, then you can try to fit them to an orbit. So here's observations of 3 observations on, I can't even read these dates from here, but they're about a week or so apart. And once you can fit them to a preliminary orbit and it looks good, then you don't need to make these kinds of geometrical arguments anymore. You can actually use the orbit to predict where it will be in the future or where it might have been on previous nights. And so that process then goes pretty quickly, and here's one such new object. So points on, you know, here, then it hits this gap for a little while, comes back over here, and in fact this one was picked up at the prior opposition the year before at not so many points. So this is that ellipse now that doesn't quite close because the thing also got a motion of its own of a degree or so per year. So this is one of our new objects. But I think a picture is worth, you know, is maybe more fun anyway to look at. So here's our mosaic. And raw astronomical data looks really terrible. You know, this is what a raw image looks like. There's bleed trails from bright stars, and one of the CCDs died, and the amplifiers have different gains, and so the grays are different, and so on. So this all gets, you know, taken out in the, not that one, but these artifacts all get taken out in the image processing. So that's a image of one of those fields on one night. For reference, there's the full moon. So it's a very wide field instrument. So you probably can't find the Kuiper Belt object in this picture yet. So let's zoom in on this particular chip up here. So there it is. There's that bright star up in the corner. And you probably still can't see it. So let's zoom in the region near this bright star. There it is. And maybe still can't see it. So let's zoom in kind of into the glare right here. And of course, you still can't tell because these things look point-like. You know, on any given night, they just look like a star. The thing is, was it there before, and does it move in the right way? But that's not a star. That turns out to be an object in the Kuiper Belt. This was actually the first one we found, me and the students that summer. So we got really excited when we saw this because you look there, and there it was, and we found the image of the same area on one of those other visits, and there it's not. See? So there it is. There it's not. And this was what difference imaging did. So the template image, the search image, and when you subtract this from that, you get that. And it connects to a bunch of other points, and we had a nice one before. But movies are even better than still pictures, and so what I'm going to show you here is an animation. So there's the size of the full moon again. Here's these 3 of the 10 fields kind of close together on the sky. And this is going to be a movie that starts nearly as soon as we started taking data in November 2012. And then we're going to go forward in time, and objects will appear in this thing as when they are first observed. We'll see red dots, and then a line to connect the orbits. And so you'll see, even though these things all have very different orbits, their motion is all to kind of first approximation the same because it's dominated by the motion of the Earth. So here is kind of a couple years of search and discovery for these things. So there they go. So now another orbit the sun, we start a new season, a whole bunch more things show up. Some of them get observed for a second time. Then the second season starts and new things wander into view. Some of the old ones wander off. Okay, so there's a bunch of things, and we've since then added a number more to this list. I feel, someone always asks, what do these things look like? Can you see anything? They look like that, and that's only because the size is only because the air and the optics spread the light out. They're completely white light. Of course, they really look and as bright as a candle, about 40,000 kilometers away. These objects are typically 22nd to 25th magnitude objects. So, of course, they really look something like that, but in all these cases, we'll probably never know for sure. So here's where the 34 objects we found to date sit on this graph I showed you before. So we found half a dozen new Plutinos, a couple of centaurs, things that are actually inside Neptune's orbit, a couple of Neptune Trojans, objects that orbit in a one-to-one resonance with Neptune, 60 degrees ahead of Neptune. They kind of orbit a point 60 degrees ahead of Neptune and go in this interesting kind of kidney bean shaped orbit that I can tell you about it if you want to know more about that. And here's an up-to-date list on my webpage. These supernova fields are well off the ecliptic plane, and so we're kind of by definition not looking for those cold classical things. We're looking for the high inclination things. That's just where the supernova fields happen to be. So with one exception of a thing we found elsewhere, they're all probing this scattered, excited population. So these are the dynamically kind of disturbed objects that have had some sort of interaction with Neptune in the past. And then I think I'll show you this plot too. This is how far away were they when they were discovered in AU as a function of their estimated size, assuming that they reflect about 5% of the light that's incident on them. So these objects are between 100 kilometers and maybe 5 or so 100 kilometers in size. They range in observed brightness from 22 minus a little bit up to almost 25th magnitude. And these contours here show you how bright an object would be at different distances. So what this is saying is, okay, we can see 24th magnitude objects, so how far away could we see what kind of an object? If you follow the 24th magnitude line down, you see at 80 AU, we could see an object that's about 700 kilometers or so in size. Actually about 600 kilometers in size. So we are sensitive to quite relatively small things. Certainly much smaller than Pluto. Let's see, I think so. There's our Neptune Trojans, and here's another movie of these guys. So there are not so many Neptune Trojans. There's like 6,000 or some known Jupiter Trojans, but only about 11 known Neptune Trojan. So here's a simulation showing the Sun, Jupiter, Saturn, Uranus, Neptune, and then the Neptune Trojans that lead Neptune and the Neptune Trojans that trail Neptune. There's more of them up here because this is along the line of sight to the galaxy and it's just hard to find stuff. But we're going to look at this in the frame co-rotating with Neptune. So imagine kind of being in a spaceship, looking down on the plane of the solar system and hovering over Neptune. So here's what these things do. So Neptune is stationary, the other planets are going around inside. And these Trojans follow these kidney bean-shaped orbits that are centered on a Lagrange point, 60 degrees ahead or behind Neptune. This one wanders way, way ahead. The two new ones that we found are the slightly lighter yellow. They're interesting because they were probably captured into resonance. They were probably out there when Neptune arrived at its present location after migrating outward early in the history of the solar system, and sort of captured these things into resonance and kept them there. These orbits we've studied on timescales of 1 billion years or so, and they look stable. They're not going to get kicked out by Jupiter. So now I want to talk about this one. And I'm glad you didn't put Planet 9 in the news, because it gives me a chance talk about it. So how many of you saw the news that there may be a 9th planet out there? Okay. So this thing is part of the evidence for Planet 9. So this is obviously our most distant object. There are very few other objects that are more distant than that. The ones that are tend to be things that come much closer in, like these would almost be comets, these things with such high eccentricity. So this one you can see has a perihelion of close to 40, it's near that curve. So it is definitely a trans-Neptunian thing on a very distant orbit. So this is 2013 RF98. There it goes. This is a discovery sequence of images of this thing, a nice galaxy cluster there in the background. So it's got an orbital period of nearly 6,000 years, inclined 30 degrees to the plane of the solar system. It's within 36 AU of the sun, and it just reached perihelion a couple of years ago. So there are only 4 other objects in the solar system that we know about, including 7, that are not Neptune crossers and have longer periods than this one. Now, the interesting thing, and the whole basis for the hypothesis of Planet 9, is that these objects have orbits that are aligned in a statistically unlikely way. I think I'm gonna, actually these slides are out of place. We found another Pluto. It's, here's Pluto, here's the thing we found. It's kind of Pluto-like. Here's what Pluto's do. That's the 3-2 resonance. So we do these kind of cartwheels around Neptune. This simulation was made by a high school student I worked with last summer. Integrated these orbits and made this nice animation. Okay, so sorry about that. So here's the thing. So we can talk about the orientation of that ellipse, relative to kind of some arbitrary place you say is like 12 o'clock. And the orbits of these most distant objects are all roughly aligned in the same direction. The ellipses are long in the same direction. So here they are. This thing is called the argument of perihelion. And the thing is, though, that these orbits slowly precess. These ellipses kind of clock around the sun on timescales of hundreds of millions of years or more. And they do so at different rates, depending on how much time these things spend close enough to even talk to the inner solar system. And so, if the 4 giant planets are the only things really perturbing these orbits, then this current alignment does not persist over timescales comparable to the age of the solar system, billions of years. So maybe it's just a coincidence. Maybe we just happen to be living in a time when these things are aligned. But it turns out they also align in another angle, and that means that these orbits actually kind of physically lie in a plane. You can argue about how statistically likely or not that is, but it looks weird. It looks like something you might want to try to explain. See if you can come up with a dynamical explanation of that, something that might stabilize it. So here's the picture. This was actually put out by the Caltech PR apparatus last week in the course of talking about Planet 9. So here's the 8 or so most distant objects that are kind of aligned. These also, if you turn this picture on its side, you can see they're also kind of in a plane that way. Here's our object. And what these guys have, these 2 theorists at Caltech have worked out through some really clever computer simulations is that if you have a planet of about 10-ish Earth masses in an orbit that is anti-aligned with these things, in a moderately eccentric orbit at moderate inclinations, it can actually kind of shepherd these things into an orbit that looks like that. And it's stable. So that suggests you should maybe go look for a thing like this. Here's some of the details of the simulations they ran. You can't see these, but this proves they did a lot of work on computers. 700 AU, 7 to remember is it has a perihelion of 80, so this thing is way out there. Anti-aligned. So it makes this prediction that it can stabilize these things. That's cool. But it also makes 2 other predictions that they weren't expecting to make, and so that also makes it cool and testable. So It predicts another population of Sedna-like things, but that are aligned with the perturber instead of anti-aligned. And it predicts a very high inclination population, like maybe even perpendicular or even retrograde orbits that may come in further to the solar system. That might not be so distant, but have very eccentric orbits that take them inside Neptune. There are a few such things known, and their origin is a little bit of a mystery. So maybe that's the reason. We look way off the ecliptic, and so if there are these kinds of things, we're in a good position to find them. So, my own feeling is we may or may not find Planet 9. But we will certainly find lots of objects that belong to dynamical classes that can test this model. We'll find, more high inclination objects. We will find, I hope, more things like RF98 that will either cluster in these variables or not, and either constrain the theory or eliminate the need for it. So that'll be exciting. So we're just finishing our third of 5 years on the sky. It's been a terrible year. The same weather patterns that have produced this nice mild Michigan winter have produced observing weather that looks like this in Chile. There's been an enormous amount of precipitation and clouds. We've lost more nights to clouds this year than all previous years of the survey put together. It's the worst August and September, probably by now the worst season in the history of the observatory. And when it hasn't been raining or snowing or cloudying, there's been earthquakes. So this big earthquake in Chile on September 17th, and we were off the sky for a week because of that. These are the guide stars shaking during one of the aftershocks. It was just an aftershock. And here's the sea level of the nearest port city. You can see that the ground was oscillating with an amplitude of about 6 meters. So it's been a weird year, and actually this has made the case. This is helping us make the case for a 6th year of the survey. So it may not be all bad. So despite all this, we've found a number of new trans-Neptunian objects in these supernova fields, including a possible dwarf planet that's 600 kilometers out, I think. So I've talked so far about the supernova fields, and I just want to wrap up by saying that the real action is going to be actually extending the search for these things out into the full 5,000 square degrees of the wide survey. It's much harder to do for a couple of reasons that are mostly technical. Because we only visit each area on the sky in the wide survey a few times per season, the task of looking ahead and trying to connect the dots is much harder. There's many more dots to try to connect when you extrapolate over a longer time baseline, but computers are good at that. There's no difference imaging in the wide survey right now, but that's being developed. So we're, I'd say, probably a few months at least away from first results in the wide survey. But when we do, we will be, this is some measurement of kind of relative sensitivity compared to earlier surveys, something like 30 times more sensitive to high inclination, these hot, dynamically disturbed KBOs than any previous survey. And, in terms of raw numbers, 500 to 800 new ones, I hope. We've actually found the first couple of new objects in the wide survey. There's one of them, moving over a period of a couple of hours one night. They make these funny loopy patterns like this. There will be many more objects, about 1 per square degree at least near the ecliptic. So I'll go back to where I started. Here's Pluto now, not the little dot in Fly Tombaug's photos, but this beautiful up close thing. And for all these reasons, we are starting to. We are now dealing with a wealth of new data that is shedding all kinds of new light on the Kuiper Belt. And they come from space-based missions that are going up close to one or two particular things. New Horizons is probably going to have a second fly by a small Kuiper Belt object in a couple of years. Won't get pictures like this, but we'll start to see at least some detail on a typical Kuiper Belt object. But this kind of data from space is complemented by wide, deep surveys from the ground that will statistically analyze hundreds more new objects. And so, what I'll conclude by saying is that this trans-Neptunian region is this, really it's a whole new zone of the solar system that has not been well understood and explored up until now. And the most distant ones display a pattern that is at the very least, quite interesting and in want of explanation. And perhaps a super-Earth is the explanation. I don't know if we'll find it, but we will find lots of things that can help us test that model that are, testable in science, includes ruling it out. But if we're lucky, we might find it. So I want to conclude by thanking the people I work with and the people who help support this research. In the US, it's supported by the Department of Energy, by the National Science Foundation, and the corresponding national funding agencies in the UK and Spain and Germany, Brazil, and Switzerland. And I am really especially privileged to work with a lot of great students at the University of Michigan. So if you want to learn more about this stuff, you can go to our webpage at darkenergysurvey.org. We have a blog, darkenergydetectives.org. We're on Facebook, we're on Twitter, and the nitty-gritty of minor planets is at the minorplanetcenter.net. So, thank you all very much. Questions, anyone? Yes?
Very silly question, but are there any protocols yet for naming TNs?
Oh, I'm so glad you asked. So naming these things. So there's rules. The International Astronomical Union has the power to take planet status away from Pluto, and they certainly have the power to approve names. So for main belt asteroids, they can be named after practically anything. They can't be named. They can't be named after current political figures. So you can't name one after Donald Trump, or you can send him there. You can't name them after political battles that are within the last 100 years or something like that. But apart from that, you can name them after ordinary people. You can name them after authors and poets. But in the Kuiper Belt, there are special rules about what names are allowed, and I hope they will revisit this because there's now enough of them that it's a little bit constraining. But the rule is that Kuiper Belt objects need to be named after deities associated with creation. They are, after all, primordial remnants of the solar system's formation.
And not a Greek warrior princess.
Not a Greek warrior, but a Disney character is allowed. And actually, objects in the 3-2 resonance, like Pluto, must be named after underworld deities, like Pluto. So obviously the Greek and Roman mythologies have been picked over, for decades. But I think it's interesting to think about reaching into the mythologies of, say, the native peoples of the Great Lakes region. If they want it, it's a politically fraught thing to just kind of appropriate their culture, but that's something I'm interested in exploring. They have to be observed over enough oppositions that their future positional uncertainty drops below a certain threshold, and most of our objects are not there yet. But after about 4 or 5 oppositions, we expect to have many nameable objects.
Excellent.
Yes, sir.
I'm curious about why you look for supernovas. Is that color calibration for redshift?
It's close. So there's a certain kind of supernova. So this is really a cosmology program. So there's a certain kind of supernova that is what's called a standard candle. A type 1a supernova is a star that always, this particular type of supernova always explodes with pretty much the same intrinsic brightness, which means that if you can observe their apparent brightness, you know how far away they are. And so what we do with these supernovae, which are all exploding at a safe distance from Earth, is to make the same diagram that Hubble made. Hubble plotted distance versus redshift, or distance versus velocity, and got Hubble's law. So the more distant objects are expanding faster. Hubble was using individual stars in relatively nearby galaxies, and so he couldn't draw that diagram over a very long baseline. But type 1a supernovae, while they last, are about as bright as their whole rest of their galaxy. So they can be seen over cosmological distances up to half the age of the universe. So what we're doing with those, and the whole way dark energy was discovered in the first place in the late 90s, was that the most distant supernovae actually turned out to be fainter than you would have expected, unless the universe has accelerated. I mean, if the universe has expanded more than just a universe that is slowing down, would have been expected to do. So that's the purpose. We're going to discover about 3,000 of those by the time the survey is done. Question here.
Yes, do you think there would have been a New Horizons mission if Pluto had been demoted as a planet before the inception of the mission?
I think there probably would have been. I mean, that's a good question. I think regardless of what you call it, you know, it's Pluto. It's a very interesting thing in the outer solar system.
We've known about it for a long time.
We've known about it for a long time. It has, you know, obviously the fact that it is no longer formally considered a planet hasn't, you know, diminished its hold on the public interest. So I would, you know, although you may know that New Horizons, like, kind of was on verge of being canceled a number of times. You know, I think the biggest threat to New Horizons was not that Pluto might have been demoted a little earlier than it was. It's the usual NASA budget process. Yes?
You know, one of the things that in the news thing I did with the supernova, the early part of it, what I gleaned from that was something that you're referring to, that the 2As are not a problem for us, but the 1As are, because we really don't know exactly where they are. Is that what we're finding out as well?
No, it's the type 1As are, they, you know, they all occur in just kind of at random in galaxies, and there's a little bit of dependence on the type of galaxy, but that's not super important. The difference is that a type 2 supernova is the core collapse of a massive star that's exhausted its fuel. The type 1As that are of interest, and the reason those aren't standard candles is there's all kinds of different masses of stars that explode in that way, but it's different every time. The type 1As are a special, completely different kind of supernova where you have a white dwarf.
Right.
So this is a kind of...
I'm saying the explosion that results from that is more likely to affect us than one from the 2A.
Well, so the 1As are intrinsically more luminous than the 2s.
Right.
So that means that the safe distance for 1As is actually further away than for type 2s.
Okay.
Yeah. Yes, sir.
Yeah, what's the altitude like at?
We're about 7,000 feet, so it's not that bad. I mean, if you've ever been to Denver, you know, it's not, it's a little higher than that, but it's not so bad.
So it's not a matter, it's not a problem acclimating to the...
No, I mean, different, you know, some people have a little, you know, bit of lightheadedness the first day or two. It's never bothered me. You have to, you know, walk up a hill about a half a mile to get, or you can drive it, you know. You can walk a half a mile from the dorm up to the telescope, and you get a little short of breath the first day, but it's not that hard. Yes, sir.
If you take the orbits of some of the that have relatively well-known orbits now and extrapolate them way back, you learn something about their history?
Yeah, so there's, you know, this kind of thing has been done. You know, there's a relatively well-supported model of how not only the Kuiper Belt, but kind of the outer solar system in general got to be where it is. It's based on, you know, a lot of computer simulations, including of those orbits. It's called the Nice model, after the city where some of the people work. And you know, so it kind of suggests that the solar system started out more compact, and that as the giant planets grew, they lost angular momentum and migrated outward. At some point, Saturn crosses the resonance with Jupiter, and all hell breaks loose. But as the giant planets migrate out, they scatter most of the mass that becomes the Kuiper Belt out of the solar system, and what's left behind is about 1% of that outer stuff. So that's the model. You can't do it quite as directly as taking specific objects and actually integrating the orbits back 4 billion years, because that you lose that kind of resolution after that point. But that's the basic idea.
We have time for one more question.
Okay.
Part of the program is trying to figure out the reason for the expansion of the universe. Do you think we're any closer to figuring out the rate of expansion of the universe?
Well, the rate of the expansion is very well known. So that's essentially the Hubble constant, and that's now a pretty well determined constant. What is less well known is what is...
As you go up farther, the rate at this point versus farther out.
Yeah, so we know it's accelerating. So we know that the further away you look, the more expansion has happened. We know about when acceleration became important in the age of the universe. The universe initially was not accelerating, it was slowing down, but it kind of flipped the switch at about 6 billion years ago. So we know that. What we don't know is what kind of an underlying theory best accounts for that. So the simplest thing is to literally add one term to Einstein's equations for general relativity that corresponds to an energy density of empty space, a non-zero energy density associated with every cubic meter of empty space. And the constant term that multiplies that piece of the equation could produce the universe we see. If so, there's just a new constant of nature. It's called the cosmological constant, and maybe that's all there is to it. But, you know, as physicists, we like to think maybe there's some kind of dynamical explanation. There's a deeper theory that might explain inflation as well. So what we don't know is if acceleration is consistent with that constant, or if it's behaving in some more complicated way, or if general relativity is just, you know, needs to be modified on those kinds of scales, and we have a whole different theory. So that's the goal. You know, we will be able to at least falsify a lot of theories by the time we're done. So far, everything that we've seen and other experiments have seen is consistent with it being cosmological constant, which is, you know, apart from that constant being zero, is almost the most boring possible outcome. Okay, well, thanks.
Yes,
Thanks
thank you
again.
very much.
Okay.
After astronomy, we traditionally have gas astronomy. So like